Hi everyone, in this new introductory topics video, we will focus on functions and functional notation. A function is a relationship that associates an input value, we usually use letter X to denote it, to at most one output value, which we usually denote by Y. In other words, the function transforms x into y by using a specific rule or formula. Writing y equals f of x means that y is a value whose result will depend on the choice of x and on how function f will have an effect on it. So you can see this as x becoming y through an operation called f of x. For example, if you consider the function y equals x squared plus 2x plus 3, the function itself is the x squared plus 2x plus 3, whose outcome will depend on what value of x was chosen originally. The result will constitute the value for y. We frequently tend to write f of x equals x squared plus 2x plus 3 and forfeit writing the y, so it's understood implicitly that y is equal to the value f of x will produce. If the value of x that is chosen is 0, then the function in this case will convert 0 into 0 squared plus 2 times 0 plus 3, resulting in a value of 3. This means that the function's value at 0 equals 3, or if you prefer, that for an x value of 0, the corresponding value of y is 3. If the value of x that is chosen is 1, then the function will convert it into 1 squared plus 2 times 1 plus 3, which is 6. This means that the function calculated at x equals 1 equals 6. Or if you prefer, that for an x of 1, the corresponding value of y is 6. The relationship that exists between x and y, generated by function f, can be represented graphically in a Cartesian plane. Every pair, x and y equals f of x, corresponds to a coordinate point in the Cartesian plane itself. In our previous example, where f of x was equal to x squared plus 2x plus 3, we've already determined the coordinates of two distinct points that obey the rule. For an x of 0, we found y was 3, and for an x of 1, we found a y of 6, which we have inputted into the graph, as you can see, with 2 dots. Of course, infinitely many other pairs, x, y, obey the same rule. And if we plotted each of these points on the Cartesian plane, then a shape would begin to appear. In future videos, we'll see how specific functions have specific graphical representations. It's actually one of the main objectives of the Cal 1 course to be able to generate graphs for more complex functions using tools that we'll develop. It's also important to observe how every x value has at most one corresponding y value. This is a very important feature of functions. Any vertical line can cross the curve representing the function at once at most. So observe this first graph, and you'll notice that for a chosen value of x, there is only one corresponding y. That's true about absolute value functions as well, where every value of x has only one corresponding y value. Here's a rational expression for which every x has only one corresponding y value, aside from x equals 0, which has no image, so has no corresponding y. So it's not important that every x has a y, but that x's that are allowed have at most one corresponding y is what matters. An ellipse, for example, is not a function, because you can probably observe that for an x value of 2, for instance, two different points appear on the ellipse, one above the x-axis and one below it. So this could be called a relationship between x and y, but certainly not a function. The set of x values for which the function is defined is what we call the domain. Now, what would cause a function to be undefined? Well, there is a certain number of illegal operations we could do. Divisions by zero are one of them. Trying to perform an even root on a number that is negative is also forbidden. And as we'll see later on, logarithms cannot be computed at when its content is 0 or negative. So these are a few of the causes for a function to be undefined. The set of all y values that result from applying a function to the allowed values of x, in other words those of the domain, form what we call the range of f. Identifying the range is usually not a simple task. So back to our original example where the function we have defined is the quadratic x squared plus 2x plus 3. F of x stands for the y values we'll be obtaining from the computation at different x's. We've already produced its graph by plotting some of the points that meet the rule defined by f of x. Now there is no division by 0 in the function that is presented. There are no even roots to be afraid of, and there is no logarithm taking place, so the domain consists of all real numbers. However, notice how the range does not allow for y values that go below 2. So the coordinate point minus 1, 2 is actually the lowest point on the curve. So the range consists of all y values that are 2 or more. So one appropriate notation to write to this fact is to say the domain of f is R, so all x's are allowed, and the range of f is the interval 2 to infinity. These are implied values for y. In contrast, let's consider the function g of x equal root of x minus 3. Here is its graph. So you'll probably notice that the domain of g of x only allows for x's that are at least 3 to prevent the root from containing a negative value. The graph itself remains above the x-axis because a square root cannot produce a negative number. So the domain of f goes from 3 inclusively to infinity, and as for the y outcomes, so the range, we're looking at 0 inclusively to plus infinity. The domain of the rational function 1 over x plus 2 is formed of all x's that are not minus 2. This time we're preventing against a division by 0 by putting a restriction on the value of x and prohibiting it from being minus 2. Here is the graph, and notice how for an x of minus 2 there is no corresponding image, there is no resulting y value. So the domain is one that is broken up into two intervals, from minus infinity to minus 2 exclusively, and from minus 2 exclusively to infinity. The range happens to also be divided because you'll notice that the curve never touches the x-axis, so from minus infinity to 0 and 0 and above. Some situations can be much more complex, especially if they combine different types of functions and divisions and roots and radicals. And tools we've seen in the past, such as factoring, may end up being very useful in identifying domains. For example, let's find the domain of the function f of x equals the root of x squared minus 2x divided by x squared minus 1. Always look for restrictions that we have to impose when thinking of the domain. Are there any illegal operations that could take place? Let's start, for example, here with the denominator x squared minus 1. And recall that divisions by 0 are not allowed. Therefore, we can only include in the domain values of x for which x squared minus 1 is not 0. Here's where factoring comes in handy. So x squared minus 1 is a difference of squares, and therefore the product of x minus 1 and x plus 1 not equaling 0 obliges you to force x to be different from 1 and different from minus 1. Okay, so the denominator is not a problem aside from these two numbers. As for the numerator, we are trying to perform a square root on an expression which must absolutely remain positive or 0. So our domain requires that x squared minus 2x be greater or equal to 0. Once again, we've attacked this kind of problem in the past when we solved inequalities. And one of the best ways to approach it is to go by factoring first of all. So simple factoring allows you to split x squared minus 2x into x times x minus 2. X minus 2 has zeros at 0 and 2. And testing for signs around the zeros, we will find that x times x minus 2 does stay greater or equal to 0 to the left of 0 and at 0 itself, as well as at 2 and to the right of 2. So at this stage you're probably performing a number line and doing tests for signs to verify where x squared minus 2x is greater or equal to 0. Now we can identify the values of x that satisfy all restrictions. So remember, to avoid a division by 0, we had to prohibit x from being 1 or minus 1. To guarantee the content of the root remained positive or 0, x had to be 0 or less, or greater or equal to 2. We can visualize both of these restrictions individually at first, perhaps. So notice that the top line includes all x's aside from 1 and minus 1. In the bottom line, we've indicated the regions where x is less or equal to 0 and those where x is greater or equal to 2. Now the domain would be formed of all x values that satisfy both criteria. So in other words, where both lines have been shaded in red. So that's true as long as we are left of minus 1, to the right of minus 1 or at 0 inclusively, or we are at 2 inclusively and to its right. So you're looking for all the regions where the shaded red lines overlap, and it would be formed of these three intervals. Notice how different labels are used to identify different functions. So f, g, and h is a way of distinguishing functions from one another. But remember that in all cases, applying an x value to any of these functions will still reveal a y value. Here is an example where we have listed 4 different functions, which we've labeled as f, g, h, and k. In the graph, you also see there are 4 different curves with their different color associations. All of the functions have been calculated at minus 1 on the top left corner, and notice how each of them have distinct y values. In one case, we even have g, which is undefined at minus 1. You'll notice in the graph that function g only begins where x is at least 3. Finally, always remember that variable x is simply a placeholder that can eventually be replaced by values or potentially by entire expressions. So for instance, this function, x cubed minus 2 over x, holds the place for a number, which could be a number, could be an expression, could be an apple, could be an entire expression. So x is just a placeholder that can be replaced by more complex things than